Hi, welcome back. My name is Esther Kim, and today we're going to talk about standard deviation, which honestly isn't my favorite thing to calculate. But luckily for the SAT, you don't need to know the equation, so you don't need to calculate anything. They're mainly testing you on whether or not you know the difference between a big and small standard deviation and how a standard deviation changes. So let's talk about what standard deviation is. Standard deviation is not the same thing as standard error, but you do use standard deviation when you collect a bunch of data points or a data set, and you need to indicate how consistent your data is. So in lab or class, what you usually do is you calculate the mean or the average of your data points, but this mean doesn't indicate the nature of your data set. And that's when you calculate the standard deviation. So standard deviation is defined as how much your data set deviates from the mean that you just calculated. Some people define it as how dispersed your data is. I personally see it more as how off your data points are from the mean. So a general rule of thumb is a big standard deviation indicates that you have a lot of data points that are very far away from the mean, and then a small standard deviation indicates that you have a lot of data points that are very close to the mean. So let's go over an example. I use this example a lot when I talk about standard deviation. I call it good data versus bad data. So say that you have two scientists, scientist A and scientist B. And let's say that they decide to measure the height of the same person multiple times and then plot the data. So on the x-axis, we're going to have trials, and on the y-axis, we're going to have height in units of feet. Let's start with scientist A and say that they measure a height of 1 foot for trial 1. Let's go ahead and plot that. And then for trial 2, let's say that they measure a height of 5 feet. And then for trial 3, they measure 1 foot again, and then 5 feet. Who knows why, but this is the data, such that the mean is going to be 3 feet. So let's go ahead and make a line at 3 feet, and then also label it as the mean. Then for scientist B, let's say that they measure a height of 2.9 feet for trial 1. So let's go ahead and plot that. And then they measure 3.1 feet for trial 2, and then 3 feet for trial 3. So basically, their data points are very close to 3 feet, such that the mean is also 3 feet. So let's go ahead and draw a line through 3 feet again, and then also label it as the mean. So if you notice, both scientist A and scientist B have a mean of 3 feet, but if you look at scientist A's data, the data points are very far away from the mean. So here the standard deviation is big. So I'm just going to label this as ST is big. This is what I would call bad data, but I put bad in quotes because who knows what's going on. And then if you notice for scientist B, the data points are very close to the mean. So this is where the standard deviation is small. So SD is small. And then this is what I would call good data. Let's try one more example. This example might look familiar because it's about test scores. So we have class A and we have class B. On the x-axis, we have number of points. On the y-axis, we have frequency or number of students. One thing to note is that the mean for both of the classes is 75, so this is probably like a physics exam. Let's go ahead and draw a bell curve for both of them. They have something called normal distribution, which just means that the curves are symmetric about the mean. So a rule of thumb is that if the average or the mean is pretty obvious or more pronounced, the standard deviation is small. And this is because the data points are closer to the mean. If you look at class B, even though the mean is 75, the distribution of the data points is more widespread. So we talked about how standard deviation is about how off or how dispersed your data is from the mean. So for class B, if you notice, there are more students who are farther away from the mean compared to class A. So class B has a big standard deviation. Let's go ahead and try some problems. This problem is about heights of NBA players in inches. It says the dot plot above depicts the heights in inches of players on a professional basketball team. What would happen to the standard deviation of the data set if the lowest and highest heights were removed? So there's a cluster right here, which means that the mean is going to be closer to this area. If you knock off the lowest point and the highest point, which are kind of like outliers of the data set, there are a couple things that are happening. First of all, the mean's going to change just a little bit because you got rid of a couple data points. But the mean is still around this area. And the other thing is that the data points are getting closer to each other, so they're getting closer to the mean. Because the data points are getting closer to the mean, that means your standard deviation is getting smaller, or in other words, your standard deviation is decreasing. So this table has countries and GDP, and it says the table above shows the 10 countries with the highest GDPs in the world in 2018, as well as their GDPs in trillions of dollars. If the United States were removed from the table, how would the mean and standard deviation of the GDPs change? This problem is more like what you would get on the real test because it's asking you about standard deviation, but it's also asking you about the mean. Let's start with the standard deviation. So they're asking you what would happen if you took this 20.4 and got rid of it. So if you get rid of it, then the data points are one step closer to each other. So the standard deviation should be getting smaller or decreasing. This is a down arrow. Let's talk about the mean. So this 20.4 is really big. It's almost like dead weight. And what it does is it pulls the mean towards its side. So if you got rid of it, that means that there's no pull and the mean is only being calculated by these numbers. So the mean is also getting smaller, or in other words, is also decreasing. The table says birth weights of piglets in kilograms. The table above lists the weights in kilograms of a litter of newborn piglets, of the mean range and standard deviation of the values listed, which will decrease if the 0.98 kilogram measurement is removed from the data. The problem is asking for a lot of things, and I'm going to put them in a specific order. So first we have standard deviation, then we have mean, and then we have range. Let's go ahead and make a table, and then let's look at standard deviation. So they're asking what would happen if you got rid of this 0.98. If you notice, the data points are getting closer to each other, so the standard deviation is decreasing. Now let's talk about the mean. So 0.98 is less than 1, so it pulls the mean in this direction. When you knock this number out, the data points are now all greater than 1, and so when you calculate the mean, you're only dealing with these numbers, which means that the mean is increasing. The definition of range is the biggest number minus the smallest number, so let's do it before and after. So before, the biggest number is 1.73, and the smallest number is 0.98. You don't have to do any calculations. So afterwards, they said to get rid of the 0.98. The biggest number is still 1.73, but now the smallest number is 1.13. Again, you don't have to do any calculations, but you can see that the new range is smaller than the old range, which means that your range is decreasing. All the problems that we've dealt with so far only had one data set, and now we're dealing with two data sets. So let's look at the graph. On the graph, we have days for the x-axis, and then we have average temperature in degrees Fahrenheit for the y-axis. We're looking at two cities. We have city A and city B. The graph above gives the average temperature in degrees Fahrenheit for city A and city B over the same 7 days in March. Let MA and SA be the median and standard deviation of the average temperature for city A, and let MB and SB be the median standard deviation of the average temperature in city B. Compare the medians and standard deviations. For city A, we have the median labeled as MA and standard deviation labeled as SA. Similarly, for city B, we have MB and SB. Let's make a chart. So we have city A and we have city B, and we're going to look at their standard deviations and their medians. Let's start with standard deviation for city A. The temperature on the first day for city A is around 51 degrees. Then it drops down to 49, and then it goes up to 50, then 54. So the data is pretty consistent, and it's around 50 degrees Fahrenheit. Let's say that the mean is around 50 degrees and draw a line. You can see now that the data points are very close to the mean, so here the standard deviation is small. For city B, the temperature starts at 59 degrees Fahrenheit and then pretty much drops all the way down to 39 degrees Fahrenheit. So the data is all over the place, there's nothing consistent about it, so the standard deviation here is big. For city B, the data points are so inconsistent that you don't really need to compare it to the mean to know that the standard deviation is going to be big, but let's go ahead and draw the mean. Most of the data points are below 50, so the mean is probably around 40, 45, so let's go ahead and draw a line. Again, here you can see how far away the data points are from the mean. So again, the standard deviation is big. So for standard deviation, city A has a smaller deviation. We can write SA is smaller than SB. Let's talk about medians. The median is your middle data point if you ordered your data set from low to high or high to low. If we look at city A's data, it's not in any order, but it is clustered around 50 degrees Fahrenheit, so we could say the median is probably around 50 degrees. On the other hand, for city B, the temperatures actually look like they're arranged from high to low. So the middle day, which is day 4, is a good estimate for the median, which is going to be around 40 degrees Fahrenheit. So looking at the chart, city B has a smaller median, and we can write MB is smaller than MA. So this is the last problem. Let's go ahead and look at the dot plots. So we have fish gummy candies and we have worm gummy candies, and the plot is measuring the distance traveled in inches. One thing to note is that the scales are different. So the fish gummies start at 45 inches and the worm gummies start at 65 inches. Let's go ahead and read the problem. It says a class used catapults to launch 2 kinds of gummy candies. The dot plots record the distances the gummy candies traveled. Compare the standard deviations and the means of the distances traveled of the 2 kinds of candies. Let's label the standard deviation for the fish gummies as SF and the mean as MF. And then do something similar for the worm gummies with SW and MW. Then let's make a table where we have fish gummies and worm gummies, and we're going to look at their standard deviations and means. Let's start with the standard deviation for fish gummies. So in example 2, we talked about how when the mean is more obvious or pronounced, it means that the standard deviation is smaller because the data points are clustered. So if you look at the fish gummy data, there's a huge cluster right here, which heavily influences the mean, and the mean is probably around here. The worm gummies also have a cluster, but it's broader and it's right here, and the mean is probably somewhere around this area. Because the data points are more clustered for the fish gummy, the mean is more obvious right here, so the standard deviation is going to be small. And the standard deviation for the worm gummies is going to be big because the data is more spread out. So we can write SF is less than SW. So another way to see that the data points are more clustered for the fish gummies is that it starts at 45, but the data points end at 105. So the range is actually from 105 to 45, which is equal to 60 inches. But then for the worm gummies, it starts at 65, but it goes all the way up to 155. So this range is bigger. You have 155 minus 65, which is equal to 90 inches. So the whole point is that the fish gummies have data points that are more close to each other, and the worm gummies have data points that are more spread out. Let's go ahead and talk about the mean. So the mean for the fish gummies is probably around this area. So that's about 80 inches. 80 inches on the worm gummy scale is right here, which is definitely not the mean. So for the worm gummies, the mean is probably greater than 80 inches, which means we can say that the mean of the fish gummies is less than the mean of the worm gummies. And that's it. So hopefully you found this helpful. Your comments, questions, and requests are always appreciated. Thank you so much. See you next time.